So I'm sure everyone's getting a little tired, so I'll try and get through these slides pretty quick. There's a party happening at 6, right? So I'm here to talk about continuous optimization. I know I got you guys on a hook that was like how Ancestry saved 2 times in Kubernetes. And that's true, and I'll get to that as we kind of dive into the infrastructure at Ancestry. So you'll get to learn a little bit on how we run, what our infrastructure looks like, and kind of where we're going with this continuous optimization aspect. So just quickly, a little bit about me. I started my career over at Research in Motion. If you don't know who that is, we rebranded eventually to BlackBerry, kind of invented the smartphone. We played at scale, right? We had dozens of data centers globally. We had a dozen more network nodes globally, from Singapore to Amsterdam to North America. And I managed the global capacity team there. After that, I moved over to Ancestry, as you obviously know. And there I run the cost governance team, the cloud cost governance team, which is responsible for changing the culture at Ancestry. As we have moved everything into the cloud, we've now exposed all our costs, and we now have developers having to manage costs along with their infrastructure. So, how do we do that at scale? Well, we implemented some artificial intelligence here. We work on different tracks in different spaces, but yeah, we're headquarters out of Lehigh, Utah, and we also have offices in San Francisco and a few other offices globally. So, if you're interested in what we do, by all means, we're always hiring. But you're here because you want to learn about AI. Now, we're not here to obviously talk about the world-ending sort of AI. We're here to talk about the kind of artificial intelligence that helps us out in our day-to-day, and that is also not how, but a little bit more about the aspect of how do we take away the work that you do on a daily basis and get an artificial intelligence around that. And I'll get a little bit of that because most of you, I assume, are either developers, engineers, or some sort of infrastructure managers that you manage containers, whether that workload is in AWS, in GCP, or Azure, or on-prem. You manage these containers and you want to get the most out of them, right? We all struggle with this problem, right? How much overhead do we keep? How do you auto-scale and all that other fun stuff to make sure that you have 100% uptime, but you're not wasting money in the process. So what do? Well, you watch graphs, right? Or to some extent watch graphs to maintain, obviously, some capabilities of whether or not your system has spikes. You dampen those spikes when you find those spikes, or you adjust for those spikes with extra capacity. Back-end workloads are a little easier, right? Your system goes up and then it goes down. You can scale through those, tend to be a little easier to manage. But if we get rid of the engineering aspect, what we can do is we can bring in kind of a neural network, machine learning sort of aspect to this that both understands the underlying infrastructure. So whether we're all in AWS, so it's EC2, and we run on Kubernetes, so obviously our container spaces. And also, we do a lot of infrastructure as code, right? So we have more at our disposal than just the resource type that you're dealing with. So that includes whether that's socket connections to your databases or Java heap size variables. And we'll get into a little bit of that. But the idea here is that at a high level, we connect our monitoring to the machine learning kind of algorithms and AI to process what the system is doing and then make changes to the system at faster rates than humans can, right? Like, you can do it. There's no issues here with any engineer doing this, except that our problem at Ancestry is that we have hundreds upon hundreds of applications that talk to each other. We have 80 plus agile teams at Ancestry, 500 plus developers, and I can't scale this with my team of 4. So we look at ways to optimize large systems without having to embed ourselves into these teams and teach them these practices. What we're trying to do is get in front of it, allow them to install this application. We use an application called Optune. It's from Opsani that basically embeds itself into our infrastructure and we allow it to make changes to little bits of our infrastructure. And I'll get into the details there. But the idea here is, of course, if you can get the system to understand what's happening, you can then reduce the footprint and double your performance. And by virtue of that, it decrease the amount of capacity you need, right? And so that's in a nutshell what I'll talk about. And I'll layer in kind of Ancestry and what we do. If you don't know what Ancestry does, we are a genomics company that does family trees along with DNAs. You might have seen some of our commercials. We're big in the 65 plus year category if your grandma's on it 8 hours a day. The younger crowd's a little off, but we're working on that, and we have a lot of mobile stuff in the pipe. But this is a representation of our infrastructure. It's a logical infrastructure, a logical representation, but I tried to draw it in such a way that it makes sense. One is it's representative of the size of the components we have, and then allows me to drill down into the component levels so that when we have conversations, if you have questions about how we've implemented this, we can get to the aspects. So on the one side, you'll see I built a little bit of a gradient, and we'll pull back a little bit on our infrastructure here. If the front-facing wall there on that side is our security team, right? They tend to keep us safe. It's the ever watchful eye of Sauron. Tony, our CISO, would not appreciate that joke. But inside, we have tons of services, right? I don't know how any of you are laid out, but at the end of the day, we have something like 50 services we maintain. And I'll get a little bit into that as I pull away our front end. So the front end there was kind of obviously our Ancestry.com. We also have other properties within Ancestry like newspapers.com and Fold3. We do collections work, right? And so when we do collections, we have some of our content pipelines. We won't talk about that. We have commerce. We have data warehousing. We have data science teams. And we'll pull some of those aspects away because that's not what we're talking about. But rest assured that we spend millions within Kubernetes. And even saying that, I'm not allowed. But we have lots of money to be saved within the space because when we take a look at our overall infrastructure, we don't have 90% CPU utilization as we wish we all did. But we know that there's room to save. It's just that as we dive into the system, you'll notice that there's a ton of complexity. Some of our larger systems are actually some of the systems that I'll dive into. One is called DNA matches, and that's the POC we did. But on top of that, we have a few systems called Big Tree, trees and stuff. These are systems on the back end that help customers obviously build their family trees. And then systems that obviously do DNA processing and stitch some of those things together, right? Our bread and butter is not that we do content, it's that we do content and we stitch that content with other content like genomic data and user-generated content. And that data is constantly living in this space, and that's why we have a fairly complex system, even though we're not at the scale that BlackBerry or Google or Facebook tend to act. But we do have exponentially growing systems or near exponentially growing systems, right? You match to your cousins through generations, and we go as deep as your 8th cousin. And if you can imagine, an 8th cousin match is basically almost everyone, right? Now we tend to not go down that far, but that's the science in it, right? We can we can actually figure out where you match with cousins down the generational lines. So as we pull away some of those back-end systems, we get down to our DNA matches. The top box there will actually represent our operational systems. So that's logging, monitoring, our CI/CD pipeline. All the things that we tend to standardize and try and generalize on will be the top of that box. And as we pull that away, we end up with a service called DNA Matches. So DNA Matches, as the name suggests, takes the genetic data that you provide as you spit into a tube, and we process that in a lab. We have algorithms that basically will match you to cousins and give you hints based on some of those genetic markers. These hints will come to you in emails in the system. And it's a living system because, one, the science grows and expands, and we learn new things all the time. But also, as we match more people and have more subscribers, this system grows at near exponential rates, so much so that at our scale, even though we're only a billion-dollar company, we have complexity here that rivals Facebook, right? Facebook has 2.3 billion subscribers with an average of 300 plus friends. They have less connections than we do in that DNA Matches database. So as we pull away our infrastructure, we'll focus just on DNA Matches. It's a simple sort of system at the infrastructure level. It's complex at the science level, but we have a database backend and storage with some compute to shard that data, keep it in memory, make it searchable and accessible to customers. And then we have our Kubernetes applications on top of that. Then we bring in one more thing. We bring in from the infrastructure piece, we'll bring in our CI/CD and monitoring suites and logging on top of that. And that, in a nutshell, is our DNA Matches service. This is pretty kind of accurate in terms of like a logical representation of what that looks like. And from there, we actually want to focus on one application for our POC. This is the matches portion of the application, and this is it doesn't do any ingesting of large systems. What it does is it takes a request and sees what a new user is and who they're matched to, changes those in the tables, then changes those cousins, and then those people. And so it's processing constantly as we add subscribers to the system. Now, we run, obviously, Kubernetes with this application, but what we want to do is we want to pull away some of that information because it's not prudent to this current discussion. So we'll pull back and just focus on this system. So we have containers or pods within this application, and we want to go back. We want to go one level deeper, and that is to the kind of atomic level, and that is one pod, right? And so what we do is we actually pull out, we create a canary, right? I'll assume that most companies or most of you will have some sort of deployment pattern. We typically, about half our teams use a blue-green deployment, and half our teams use kind of a canary smoke deployment. Depends on the size of the system and how resilient it needs to be and how those dev teams have approached it. We have adopted a DevOps mentality, though we do have problems in the space where some teams do it one way and some teams do it another way, and so we kind of have to figure out multiple ways to solution something like this. So we use a canary load, right? What we do is we connect it to our CI/CD platform. We use Opsani to gather the metrics for it, whether that's Zabbix we use internally, or another APM solution I'm not going to mention, but and we monitor the canary, and then from there, once we have that, we set up secrets management so that it can make changes to the canary. We actually do this in production, since we have a hard time with some of these systems doing load performance tests, due to the fact that if we had a load performance test on this system, we would just literally have to duplicate the entire application. So we just do it in production. Now, what we can do is actually move traffic from the cluster and put a little bit into the canary, right? So if you're running 10 pods, we'll extract 1, have 9. We'll move 10% of our traffic into the canary, 90% to the rest, and we create a baseline, right? So now that we have a baseline, now we can get the machine learning to work for us, and we can then start understanding what changes, what effects the changes have on the canary against our baseline. And that's what we do. We make changes, and when I say we make changes, we actually let the artificial intelligence start making these changes, right? So the changes happen iteratively and multiple times an hour. We do 40 to 50 changes to the canary within a day. The system monitors, the system adjusts, and the system recommends paths within a set of variables that we give it. The POC started with 2 main variables, right? That's CPU and memory. And then from there, we actually added other variables to the system, and I'll get that in a second. But yeah, we added things like socket connections, right? Thread counts, Java heap size, garbage collection. This application's on Java. And so we're able to actually tune more than just the resources within this space. We let the ML AI model take over and actually start tuning multiple variables in unison, right? We, as humans, tend to have a little bit more difficult time with that, mostly because it's time intensive, right? It's not that we're not smarter than the artificial intelligence. I hope we all are. It's just that what we find at Ancestry is that as we've microserviced our infrastructure to kind of reset expectations, we're a 30-year-old company that started on a floppy disk, right? When I say we have tech debt, I mean we have tech debt, right? But we're all in the cloud, we're on Kubernetes. We adopt the technologies that's at our disposal to try and build systems that help our customers and produce better products, right? And so in that space, we found that the complexity continues to plague us, and I assume that some of you are maybe in this space that when you have hundreds of applications talking to hundreds of other applications, the permutations in this space are in the trillions, right? Now, we don't tend to play with all the permutations. We tend to play with usually the physical ones, right? Memory, network, CPU. But even at 90% CPU, you could be constrained by connections, right? There's other reasons that you have 90% CPU, so that's not necessarily the most efficient path. You could potentially gain more performance by changing other things, and that's what we do. We add more connections. Does that have downstream effects, or is it just increased performance? And we find that obviously to increase performance for us. And this is the application that we POC'd the system on, right? Our initial POC found that we got just over 2 times performance out of the system, and we were able to scale back that application, save thousands of dollars a month, right? Now we extend that, and we have been doing this over the last few months, and actually we continue to do this while I speak, and that is we create more canaries, we cover more of the applications, and we continue the process, right? Now the system can talk to other systems and continue to make changes to the canaries and give us recommendations that allow us to obviously increase performance, reduce capacity, save millions of dollars. Now, this isn't the only thing we do. We obviously have to do that. Like, it doesn't solve every single problem for us. Like, it doesn't understand the entire architecture on the back end. It doesn't know what the algorithms are being used. And the complexity in the science doesn't go away. We still have to work with our scientists and engineers to try and resolve things like, guys, this is going to be petabytes of data in active RAM soon if we don't do something about it. And so we figure out like what needs to go into back-end storage, what can get processed once a week versus every day, and try and reduce our overall capacity that way as well. But in this case, we're allowing the system to do the little things because we have hundreds of little things, right? And every time I argue with our engineer and development groups, they go, Darek, that's $5. Why do I care, right? Like, because at scale I have $5 times a million. I'm spending millions of dollars on this stuff, and I have to argue with 500 developers why the $5 actually matters, right? So I don't want you to think that like, well, you did a small thing. I was like, yeah, the small thing, but now we're figuring out how to extend this and make this approachable to our entire organization. And I have a couple guys in the back that are going to be our container developers, Cam and Hai, that are going to be helping us onboard the hundreds of developers and stacks that we have to make use of this service so that they don't have to do the thing that I'm making them do, and that is save money, but do the things that product is asking them to do, and that is build awesome features, because at the end of the day, I love what we do, but we're not always giving them the time to do the awesome things. We're making them do the tedious things, and they need to do that, right? There's no, like, I don't think anybody's got any, thoughts that like we can just build it and forget about it, right? We need to maintain this stuff. So, as we pull away, we find that like we go back out to the infrastructure, and we know that like, hey, we only talked about one service, but we have been adding more applications to the system as well, and more services. We've been covering more services, and we're finding that even the systems we've spent 2 years optimizing, we're still finding up to 50 and sometimes 60, 70% savings. In aggregate, we're at about 30% right now. So the POC was 50. We saved, half the infrastructure. But overall, in some of the systems we've spent tons of times optimizing, we're going to have a little bit of less return. But overall, that's still hundreds of thousands of dollars that we've been managing to get out of a handful of applications. Now, that's not where the magic stops. That's just kind of where we're at right now. The next step for us is a 2020 plan to start talking about actually auto-scaling and tuning auto-scaling. The biggest problem we have this year is that we moved into the cloud, and we spent 2 years optimizing, learning the system, understanding how to deploy infrastructure, all that fun stuff, and we're all better for it, but the complications have not gone away, and in fact, like I said, they've gotten more complex because we now have more systems. We've saved a ton of money. Our infrastructure, year over year, we've been able to shrink it at about 40%, but we have diminishing returns in that space, right? You can squeeze the lemon a lot when you first get into the cloud, and anybody who's done a migration into the cloud will know that you probably have very expensive infrastructure at first, and then you find ways where there's wastage and the easy things. So we did the low-hanging fruit. And now we're really focusing on auto-scaling and making sure that our system behaves in unison with the workloads that are coming in and out of them, right? So we have front-end teams and we have back-end teams, but some of those systems do continue to talk to each other, and we want to make sure that as customers come in, we're approaching our holiday season, which is our biggest kind of uplift of traffic at Ancestry. We want to make sure that the system can scale, right? And scale when it needs to. We don't want to warm up the entire system, spend $1 million for December, and find we didn't need all that capacity. That number I'm making up, but it is expensive, right? To warm up a system and just wait for the traffic to come, right? You'd rather it be able to scale as needed with the demand. And that's what we're going to try in the next year. And maybe I'll come back and kind of do a talk on how our auto-scaling orchestration has worked and how we're able to tune auto-scaling without the engineers having to be involved as well, right? We struggle with that today, like I said. Engineers know about auto-scaling, but they're not comfortable. They don't know how to predict, they don't know what to look at for prediction, and they don't know where to scale and when to scale and understand things like, oh, my provisioning time is 3 minutes, so I need this much overhead. So we're gonna work on that, and we're gonna create more like machine-learned algorithms to watch that space, and then start tuning that in unison as well. So, as I bring back everything, that's in a nutshell my talk, our implementation. How am I for time? Okay. And so we have Paul here, and I have a couple devs with me as well. So if you have any questions about this, please feel free to talk. I know this wasn't a very technical discussion. KubeCon is usually a pretty developer-heavy, open-source-heavy sort of place, but this is kind of a complicated problem for us that at scale tends to plague us. And if you have questions about that, or you have other ways to go about this, I'd love to learn the same way you do. Thank you.